So, welcome. So this is inductance. So we've done capacitance, and we found that capacitors could be used to store energy, so they could be used as batteries, but the vast majority of them are used as a filter system. The capacitor is a high-pass filter. It lets high-frequency signals through as if there's no resistance. Low-frequency signals get hammered. Okay. You can have capacitance without realizing it, just because you have wires next to each other, etc. You can make capacitors deliberately and try to optimize them by having huge areas and very small gaps and filling them with dielectrics. Inductance is, if you like, the magnetic equivalent of capacitance. It's the result of creating and collapsing magnetic fields. You can store energy in an inductor in the magnetic field. So in that respect, it can act a bit like a battery, but it's not a very good battery because you can't store that much energy in it. Alternatively, it can act as a low-pass filter. When you're at low frequencies, it's as if there's just a piece of wire there. When you have a high frequency change, when things are changing rapidly, then the inductor just beats you up. So again, we're going to find that most inductors are made for their filtering capabilities. And when we get the resistor, the capacitor, and the inductor together in a circuit, we get a tuning circuit, which will be the basis of a radio and television reception. As before, sometimes you deliberately make inductors, but there are other times when you kind of accidentally make an inductor and you've got to deal with it. So that's where we're going to go today. We say big ideas about inductance. When the current flowing through a circuit changes, that means when you turn the circuit on, when you turn the circuit off, when you turn up the voltage, turn down the voltage, whatever, the circuit induces a so-called back EMF on itself. So you're not even trying to make an inductor there. It's just an inevitable outcome of the fact that you have a changing current in time, which causes a changing magnetic field in time, which causes a changing flux, etc. So it's just a bit unavoidable. Is it significant? Depends on the current, depends upon the details of the circuit. In some circuits with big currents, it could be very significant. In other circuits, not so much. But it's going to be there. When a solenoid is used as a component in a circuit, is called an inductor and is particularly significant for high frequency current changes. It kills you at high frequency. It's transparent at low frequency. It's the antithesis of a capacitor. I don't know if that's the right word, but it does the opposite of what a capacitor does, basically. Inductors cause transient effects on current flow, just like with capacitors. So we're going to do an awful lot of stuff that we've seen before in one way or another. So let's say we have a circuit, and let's say we have a switch in this circuit. So we have a battery, and we have a resistor, and we have a switch. And I close the switch. Okay, so current flows. That current flowing creates a magnetic field. Remember what we did? We said when the current flows in a clockwise direction, we get a south. And when the current flows in a counterclockwise direction, we create a north. So the very act of connecting up this battery, closing that switch, means that the current's going to flow in that direction, which means that we are creating a south. Now, at time t equals 0, there's no current flow, and at times t equals something, there's a lot of current flow. And in between time, it's increasing. So there's a ramp-up time when the current's getting more and more. which is a strengthening magnetic field, which is just like bringing a magnetic field, a magnet closer. Okay. So it's as if I'm bringing a magnet closer, and we learn from good old Lenz's law that the circuit fights back. The circuit says, I had no flux through me to begin with, I want no flux through me now. You have just put a whole bunch of flux through me, I'm going to fight back. So with the south pole, so with this south pole, what's happening is my current's flowing that way. I use the right hand rule, and I know that it goes in there and comes out there. So I can see that these red ones are the magnetic flux that's caused by the original current flow. There's my original EMF, there's my original flux, my original flux, my original flux. I'm just showing examples of it. And then Lenz's law says we got to get back to zero, so I'm going to create a back EMF which will cause a current which will cancel out what you've done. So the circuit creates this blue EMF which causes the blue thing, so the blue cancels out the red, and the blue cancels out the red, and the blue cancels out the red, and the blue cancels out the red. Now eventually the red's going to win because that's the real EMF. But what this rate of change dependent back EMF does is it fights the change. The bigger the change, the more it slows it down. It can only slow it down, it can't stop it, but it can slow it down. And so what should have been a sudden increase in current flow becomes a more gradual increase in current flow. It'll get there in the end, but it takes time. So we say when the switch is closed, the current driven by the battery increases in time. The magnetic flux through the circuit loop due to this increase in current also increases with time. This increase in flux creates an induced back EMF. The EMF has a sense, that means a direction, that creates a current loop that creates a magnetic field that opposes the change in magnetic flux. So the source EMF is opposed by the induced EMF, and the current increases gradually. This so-called self-inductance, this is called self-inductance. The induced EMF is sometimes called a back EMF. So this is where I wasn't trying to cause an inductor, it's just that's what is there. Now, if I can keep this inductance to be small, then I can get it so that you don't notice the difference between the two. But if I'm unlucky, or if I am working in extreme cases, then this becomes more and more visible. And the current determines the magnetic field strength, so the rate of change of current determines the rate of change of magnetic field, and so on. So the times I need to worry about is when I'm trying to suddenly get a big current, or when I have a very small, a very rapid change. So there's two times that come to my mind. One is when I'm working with power electricity. Let's say that the power has gone down in this neighborhood and they want to turn the power back on. Everybody's got their lights on. You don't turn your lights off when the power goes out. In fact, if anything, you leave more stuff on when the power goes out. Every house has all the switches closed, just waiting for power. And when they close that switch in the local substation, it's going to try and energize every house if you're not careful. And so suddenly it goes from no current flow to a tremendous current flowing. And that big current flowing means that there's a tremendous back EMF. And so they have problems with it. So I don't know how it breaks down. I don't know whether they say we can't turn on the entire city, but we can turn it on a neighborhood at a time, or whether within that subdivision they do it like street by street by street. I don't quite know how that goes, but I know they can't just turn on the whole city. You know, it's like they've got to do it bit by bit. But I don't know whether a substation can be turned on and off in one fell swoop, or whether they divide substations up into 4 bits. And so you have 4 bits that can be turned on and off independently. I just don't know. But I know they can't just turn on everything at once, because the back EMF will close you down again. So, okay, that's an issue. And then the second thing is, that comes to mind, is when you get a situation where you get extreme switching. So now we have a situation, say in a computer, and you want that data to be turned on and turned off. That's a little voltage change. So, you know, 1s and 0s get displayed as little voltage pulses and the like. And I'm going to put that into a circuit. And so what's going to happen is, because of this incredibly fast change in my signal, my d phi by dt, although it's a small phi because it's only a small current flowing, it's still a rapid change. And so in semiconductors, where all the circuits are very close together, they're in very good close proximity, that can cause problems where you can't get the speed of the chip up because of these unintended inductances that you're creating throughout the chip. And so they do things to minimize. Like, the thing they try to avoid is, they try to avoid anything on a circuit that looks like a loop. They would far sooner do that, because they're minimizing the area. When you minimize the area, remember, you know, phi is equal to BA times the cosine of the angle. If I can minimize my A, that's so much the better. So rather than having this thing connected by doing a loop, have this thing connected by doing a thin corridor, and I've reduced the effect as much as possible. Pretty much, computer chips are not designed by people anymore. They're designed by computer algorithms. You'll put in what you want, and they'll do the computer will do the architecture for you. And one of the things it's doing is it's routing things to minimize stuff like inductance. So here it's not a big current, but it's a very rapid change you want. And any slight deviation from that is going to slow down your system, and that's going to just lead to a slower chip. You don't hear so much about, maybe I don't watch I watch Netflix, so I don't get advertisements so much these days. So maybe you guys can tell me, when I was younger, in my 50s, there was the big thing was the computer wars that were taking place. Intel and AMD were AMD were the ones, and they'd have the Pentium, and so my training originally was in semiconductors. So my training was to go into just those companies, and I'm so glad I didn't go, because I would have hated it. I'm sure I would have hated it. Although learning about it is fascinating, been responsible for churning out chips, it's like, it does not appeal to my personality type, that's for sure. I would have been the worst engineer, because in the end, you know, it comes down to that thing that makes my brother a good engineer, that thrill about 0.5% efficiency, where he gets so excited, I couldn't care less about, and yet that's a lot of money in the bank for the company. So those people, when they're developing the next generation, they are pushing everything as hard as they can, and then having developed it, they are maintaining efficiency as much as they can. Neither one is my strong suit. But I had a very interesting story about, because I had some friends working on those lines, in fact, and what they said was when they bring out the next generation chip, the next one, what they will do is they will check the performance of the chips they produce. And there's a good variety. There's always some fast chips and some slow chips because of the way the statistics work. And what they'll do is they'll carve off the top end, the very fast ones, and they'll call those like the next thing. So when you were buying, if you wanted to get that next generation, that next highest speed, you were buying the ones that were where the planets lined up for them. And if you bought the standard one, you were here where the planets didn't line up for them quite so well. Do they still do that where they advertise the next generation chip, or is it all pretty much like? Do you get advertisements for computers on TVs anymore?
I would say that it would appear as if the interest has gone more towards the mobile side of things.
Yes.
And so in general, the advertisements that I know of will market the availability of information versus processor power.
Yes. Okay. So it's the market has changed its direction to some extent. I bet they still fight over it, and I bet the pressure's still there, but it's not a marketing tool for the customers anymore. So you can see how in different situations you need to be concerned about these things when they happen unavoidably. You can try and minimize it. But then there's a whole thing about when you want it to happen and then you want to maximize it. So let's think about a solenoid. So now we're deliberately winding the wire into a helix, and maybe we're putting a piece of iron inside so that we actually have this thing called an inductor. When the current flowing through a solenoid changes, a back EMF is established because of Lenz's law. Lenz's law says, I'm going to try and stop what you're doing, so that's where the back EMF comes from. The back EMF is always proportional to, well, it's proportional to di by dt. So we get my back EMF is equal to minus, well, the number of turns is going to matter, d phi b by dt squared. Whose law was that? Can you remember whose law that was?
Faraday's? Yeah.
Faraday's law. That's Faraday's law. And that equals minus L di by dt. This is L subscript. I'm sorry about the way it looks. This is L subscript. And this is L, the actual letter. This is the inductance. So minus L di by dt. That's kind of defined like that. My back EMF is equal to minus L di by dt, a bit like E equals Ri. So there's my EMF, and here's my thing, and here's my thing that's part of the system, the V equals IR kind of thing. So can you see how the L is behaving a bit like the R? So it's another possible component. L is called the inductance of the solenoid. The inductance is a measure of the resistance to the change in current. And we can say L is equal to N phi B by dt. So that's from up here. L is equal to N phi B by dt over, N phi B over I. It's taking that expression there. And it's going L is equal to N phi B over I. Okay, fair enough. The SI unit for inductance is the Henry. So 1 Henry is 1 of everything. 1 volt second per amp. The units get a bit funky. I mean, Henry is the named unit, so it hides what it originally is. But when you look at what it originally is, it's a volt, which is a joule per coulomb. So it's a joule per coulomb times seconds over an amp is a coulomb per second. So this will be joule second squared over coulomb squared, which is wacky units. Okay. Cool. All right. So we have our power supply, and we have the current going through there, and that basically sets up a back EMF, which opposes the change.
Professor, with
Yes.
regards to the last slide, I forgot to ask a question because I noticed something. I was playing with a resistor and I put voltage across it and I had my multimeter hooked up. And then when I terminated, when I opened up the switch, I noticed that the voltmeter went down slowly to 0 as opposed to immediately going to 0.
Really? I suspect that that is something to do with the sampling rate of your voltmeter. Was it digital voltmeter? It might be that in order to make the voltmeter simpler, they choose to sample, so they'll test it every now and then. But even so,
So I should try with an analog meter, you're saying?
well, then you'd have the mechanical change. Start with an oscilloscope. You know,
Okay.
yeah, that's the.
I had to buy one of those then. I know. No, but my question was basically, was it a back EMF?
So, unless it was a really extreme circuit, that means big current, then I doubt it. I suspect it's more to do with your measuring system than anything else. So we can talk about self-inductance in a solenoid. So, okay, if circuits can cause inductance in themselves, then a solenoid can cause inductance in itself. So here we have a circuit where we have the power supply, we have our solenoid, and we have a resistor. You can never not have a resistor in there, so let's just put a resistor in. And we say when the current flowing through the solenoid changes, the back EMF is established. Oh, we just did all that, sorry. And so, okay, so we have this thing, we've defined this thing called inductance, and all right, let's see physically what affects it. And I know that my magnetic field equals mu naught n over d times I, where d is the length of this thing, n is the number of turns, I is the current flowing through it. We did that in class, we did that in lab. The magnetic flux through each turn is phi b is equal to b times a, which equals mu naught n over d I times a. We just multiply both sides by a. And then if we remember that L is equal to n phi b over I, then we say, well, hold on, we got an n there. And I'll do some more. Let's have a look. So this is phi b, so I need to do n. And then phi b is going to be mu naught n over dia over I. So then I go, well, that n and that n gives me that n squared. And that a is there. And then the I and the I cancel, which leaves a d. So I get L is equal to minus mu naught. It depends on the number of turns squared divided by the area. So if I double the number of turns, I get 4 times the effect. And then I say, well, RL, the inductance, is equal to mu naught. N is the number of turns per unit length times the length. So it's going to be little n d squared over d times a. And so now we have ability to be able to cancel the d's. Mu naught n squared a times d. And a times d is the volume. This is not voltage, this is volume. I know there's so many v's kicking around. So the inductance is equal to mu naught times the number of turns per unit length squared times the volume. So a big wide one or a narrow thin one, you know, the volume is what what counts on that. We can get some similarity. I don't really care so much about that. Do not remember that equation. If you need it, I will give you it. Know what the letters stand for, though, if I give you it. Okay. So what we've done so far, I want you, I would say, I want you to know that, and I suppose I want you to know that as Faraday's law. Yeah. So no, it's not. That's not Faraday's law. I want you to know those two. And don't worry so much about that. Don't worry. Know what the letters stand for, but don't memorize it. And then let's look at this. We've been here before. Let's talk about, I can't talk about charging up and discharging, so let's talk about energizing and de-energizing. Energizing is when you put the magnetic field in, and de-energizing is when you take the magnetic field out. Just like charging was really creating the electric field, and discharging was really getting rid of the electric field. So we tend to talk about the capacitance by the charge, but really it's not about the charge really, it's about the electric field. So there's no charge to talk about here, so we've got to talk about the magnetic field. So let's talk about energizing. So we say consider the circuit below. Consider closing switch S1, so I'm going to close that, and leaving S2 open. So what happens is I apply an EMF which causes a current to flow, which causes a magnetic field to generate, etc., etc., etc. We can use Kirchhoff's rules. You know, the loop rule is equal to the EMF is equal to minus R minus L di by dt, which equals 0. And that's a differential equation, and the answer is I is equal to E over R 1 minus e to the minus. Oh, we've seen this before. There's a couple of modifications. My time constant. For the capacitor, we said I is equal to, it wasn't E over R, it was E times C. Do you remember that? Was it E times C? Let me just check for a minute. Charge equals VC. Yep. It was E times C. 1 minus E to the minus T over, what was the bit here? RC, wasn't it?
Yes, sir.
And that RC equaled tau, which equaled the time constant, and that was the time to get to 63% of where you wanted to go. This is basically the same thing. Rather than having, so this is the maximum current. I'm sorry, that's Q. Shame on me, that's Q. That was the charge. This is the maximum charge, and it's modified by this thing. This is the maximum current, and it's modified by this thing. It's the same form. We just have a different time constant. So the way to, so the thing you got to remember is that with capacitors we dealt with charge, with inductors we deal with current. And with capacitors our time constant was RC, and with inductors it's L over R. But the rest is the same. Okay. So I get this trace. If I want to de-energize, then what I do there is I open switch S1, so I'm no longer applying the voltage, and I close switch S2, and I can get this thing to just equilibrate, and I get I is equal to E over R, e to the minus T over L over R, which is what we got for discharging the capacitor. So I would remember this by analogy. I would say for my capacitor Q was equal to, it was charge equals VC, so it's EC 1 minus e to the minus T over tau, and tau is equal to RC. And then for my inductor I'd say I is equal to E over R, 1 to the minus e to the minus t over tau, and in this case tau is equal to L over R. So do it by analogy, don't do it from first principles. And just, you can put them side by side. And of course the discharging, it's just that, rather than 1 minus, it's just EC times e to the minus t over tau, and that would be for de-energizing the inductor, the current is equal to E over R times e to the minus t over tau. So. Which circuit has the bigger inductor? Can you get it conceptually? Is it the circuit that gives rise to the blue trace? So here we have, you know, what we're trying to do is we're trying to turn on our current and then have it go to a certain value and then turn off our current. That's my signal.
The red one.
And I get 2 of these traces out, and it's the red one that's the bigger inductor because it's more sluggish. It's more sluggish to charge up, it's more sluggish to discharge. It's more sluggish to energize and more sluggish to de-energize. So a bit of a conceptual question there. And if I say, let's have a look, do I give you any numbers there? I don't. I'll do it here then. So what is the time constant of a circuit that consists of a 5 Henry inductor? So L is equal to 5 Henries and R is equal to 9 ohms, and they're connected in series. So I know my tau is equal to L over R, and that's going to be 5 over 9, which equals whatever that is. 5 9s are 45, carry 5, 5 9s are 45. Is that right?
I think it's 1. No, wait.
0.55. I think that's right.
Yeah, 0.55.
Seconds. So it takes 0.55 seconds to get to 63%. To get to 63% of your current flow. Yeah, so this is I max. This is 0.63 I max, and that was 0.55 seconds. So that time constant is a really useful little yardstick to have, really. Consider circuit, 2-volt battery, so my EMF is equal to 2 volts, my inductor is equal to 4 Henries, my resistor is equal to 7 ohms. They're connected in series. What is the current flowing through the resistor 30 seconds after the switch is closed? So I would say the current at a given time is equal to my maximum current, and my maximum current is going to be equal to what's it going to be? It's going to be E over, and I'm drawing a blank now, so let me have a look. I said that it was Q equals VC, and I is equal to, what was it, E over R? E over L? And E over R. So, oh yeah, V equals IR, yeah, da 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 da. So E over R, that's my maximum current. So notice what I was not tuned into there. My basic current is E is equal to IR for current, and Q is equal to VC for my capacitance. I remembered that one, but I wasn't getting that this is the equivalent. This is the equivalent equation. And it's going to be 1 minus e to the minus t over, and it's going to be, which way around was it, L over R or R over L? For my time constant. Which way around is it for my time constant? L over R? Is there an easy way we can remember that? I can't think of one. So maybe R's on the bottom there, maybe R's on the bottom there, maybe that's, you know, hey. So that would be 2 over 7, nice choice of numbers, e to the minus, and it's going to be it's going to be 30 seconds. 30 over L, and L is 4 over R, and R is 7. So let's do this bit by bit. So I'm going to go 4 divided by 7, enter, and then do the inverse of that and multiply it into 30. And then do second E, little minus second answer. And then 1 minus second answer. Oh, that didn't work. Yeah, messed up on that. So let's go again. Not sure I'm doing this right today. Anybody got an answer for me? I'll just pass the buck. I am going to do this. So that's 30 times 7, enter, divided by 4, enter. Second E minus second answer. So we've got 1.58. 1 minus second answer. It's saying 1.
Yeah, I got 1 as well.
That can't be right. Oh, because it was such a small number. It wasn't 1.58. It was 1.58 to a tiny amount. Okay, times 2 over 7. Times 2 divided by 7, enter. So I'm getting 0.28. Now, let's just look at this. This 0.28. Hold on. What's my E max? What's my I max? I max is equal to E over R, which equals 2 over 7, which equals 2 divided by 7 is equal to 0.28 amps. So hold on, it's the same value. What's going on here? Think about it. What's my time constant for this circuit? It's going to be L over R, which equals 4 over 7, which equals 4 divided by 7 is equal to 0.57 seconds. So after I begin, I'm at that point in 0.57 seconds time, and I'm asking you what the current is at 30 seconds. So
So the maximum.
I'm way down here. I'm right near my maximum, aren't I? Yeah, because I picked the time was way too long. Yeah. Is there another one? No. So shall we just do this again with a more decent number? Let's just have a practice on it. So let's, rather than making it 30 seconds, let's make that 0.3 seconds. So I'll come down here, and then it's, so let's just do it again. That way you see the practice, and it's, so what did we say? We said that I is equal to, what was it? It was E over R, that's the maximum value, 1 minus e to the minus t over L over R. So I is equal to 2 over 7, 1 minus e to the minus 0.3 over 4 over 7. So that's going to be equal to, so I'm going to have 0.3 times 7 divided by 4, and then second e to the little minus second answer. Now that's different. 1 minus second answer gives me 0.4 times 2 enter divided by 7 enter. I'm getting 0.117 amps. So that's less than my maximum value. At that point I'm down here. Yep.
That's our question.
Yeah.
If we were to remove a resistor from that circuit and current was able to flow straight through that inductor, I'm guessing that, so at first, no, wait, at first it would slowly rise to just the maximum current, so eventually it would be the same as the EMF, correct? Going through the inductor?
So, so from a practical point of view, the actual inductor itself, so you cannot make a circuit which does not have resistance, but you can minimize it. Okay.
I guess I'm trying to say is would the inductor act sort of like a resistor?
Your inductor has got some resistance, and it will, but you will still get a time effect. You will still get a transient effect. But so it depends what you call the resistance of the inductor. Eventually,
It would even out, be the same.
you got to have some resistance in there because your maximum current is E over R, and if R is 0, then that goes to infinite.
It get hot.
Yes, yeah, very quickly actually. So again, so what is the energy inside? And what we say is battery must do work against an inductor to establish an electric current. Part of the energy supplied by the battery appears as internal energy in the resistor. The remaining energy is stored as the magnetic field. So we're getting some, heat given off here, and we're getting some magnetic field established there. Kirchhoff's laws, the EMF is equal to the potential difference across the other two components. And then we do a bit of math and we multiply both sides by I. Sorry, that's like on the previous line. Multiply both sides by I, so we get I times EMF, I squared R, oh, we've seen that before, minus L di by dt. And if we remember that du by dt equals Li di by dt, I don't think I remember that, but the rate of change of the rate of change of energy is equal to Li di by dt. The total energy stored in the inductor can be obtained by integrating. So U, the energy, is equal to the integral du, which equals the integral from 0 to I of L di di, which equals L's a constant. We get I di, which is that. And okay, we got something similar for the capacitor by looking at the, what was it, the V versus Q relationship. Remember that? Yeah. And I'm just trying to think if there's a way we can, if we were to plot, maybe I should just punt this and think about it out of class, but I suspect there's a similar thing we can do, this similar graph we can plot, which would be something like I and L or something like that. I'll think about that. Okay. So, equation. These next, I want you to know about, but I don't, if you look in the old test, you will see some questions on here, and they were always, I was never very happy with them. It's like, so I want you to know about mutual inductance, but it leads to the transformer, and the transformer we deal with later. But basically what we got here is we've got two coils, two loops actually. I've cut them in two, so we're looking at the first loop, which is in blue, and the second loop, which is in brown. And the first loop is causing a magnetic field, and that's the purple magnetic field. And that purple magnetic field has flux which goes inside the brown loop. When magnetic flux through one circuit loop varies because of a time-varying current in a nearby circuit element, we call this mutual inductance. So these two coils are talking to each other. Back here, we had self-inductance because this circuit was talking to itself. Now we're saying, well, supposing we have two loops next to each other, then they'll talk to each other. So then what's a measure of the mutual inductance? We call the mutual inductance M rather than L. And we say the mutual inductance in coil 2 is equal to the number of turns in coil 2 times the flux through coil 2 over the current in coil 1. And it's going to end up going towards a transformer, which is what we use it for. So let's just leave this. Just know that it's there. And just don't worry about this equation. Just know that it's there. You might see this equation on some old tests, but, don't worry about it. And so I can say, well, I have the EMF caused by this effect, and so on. And mutual inductance of 1 on 2 is the same as the mutual inductance of 2 on 1. And again, I don't care that much. So just know these pages are there. Know there's such a thing called mutual inductance, and it leads to the transformer, and we'll get to that later. This next bit is basically, we did the same game with capacitors. Oh, sorry, no. So this next bit is basically playing a game with an inductor and a capacitor. Now, you've got to have a resistor in here as well. The resistor is kind of like the effect of friction. It converts mechanical energy, or it converts energy into thermal energy. And at times we'd say, let's forget about the resistance, and now we're saying, let's forget about let's forget about the friction, and now we're saying, let's forget about the resistance. Can you remember the times when we dealt with a pendulum, and we just said it swings backwards and forwards? Or a mass on a spring, and we got this thing going backwards and forwards. So we didn't worry about friction for the longest time. That's the same game we're playing here. We want to play that same game. Well, let's think about it, okay? So there's no EMF here, which is a bit weird. So we got to assume that we charge the thing up to begin with, or else nothing's going to happen. So let's have some charge on this. So that's a little energy source. In getting that EMF charged up, getting that capacitor charged up, we put some energy inside it. Okay, so now these charges are free to move around, and what happens is they try to recombine through the circuit. So what we say is, assume the capacitor is fully charged, so initially all the energy is stored in the capacitor. There's none in the inductor because there's no current flowing, so there's no magnetic field. When the switch is closed, I didn't draw my switch in, but when my switch is closed, the capacitor discharges through the external circuit, which means through the inductor. A current flows through the inductor. The current reaches a maximum value as the capacitor becomes fully discharged. At this point, no energy is stored in the capacitor because it's fully discharged, and all the energy is stored in the inductor. The current flow continues at a slower and slower rate as the capacitor becomes charged with the opposite polarity. Eventually, the capacitor is fully charged and the current flow is zero. At this point, all the energy is stored in the capacitor again. So we basically take the charge on the capacitor and we flow through the inductor and charge the other way. And then we flow through the inductor and charge the other way. We flow through the inductor and charge the other way. The energy in the inductor is to do with current squared. So we get the maximum energy in the inductor, we get the maximum current flow. And so you're not going to get the maximum energy initially because there's not much current flow. And then you get a lot, and then you get little again. So can you see how the current flow changes depending upon where in the cycle I'm at? And when you have no charge on the capacitor, you have maximum current flow. And then it discharges the other way. So it's like taking potential energy, goes to kinetic, goes to potential, goes to kinetic. We have energy on the capacitor, goes to energy in the inductor, goes to energy in the capacitor, goes to energy in the inductor. It's like a pendulum. It's going to have a natural frequency. It's going to be the same old, same old. And so we tend to draw it. We can draw an analogy for it. So here, all the energy is across the capacitor, and we go backwards and forwards, and we get these thing oscillating. Mathematically. Again, there's no yellow bits on here, so that's interesting. There's no yellow bits on there. So the energy total is equal to the energy on my inductor plus the energy on my capacitor, which equals half Li squared plus 1/2 Q squared over C, which equals 1/2 Li squared plus 1/2 Q squared over C. That's interesting. Okay. Same thing. Yeah, same thing. So it's true, but it's irrelevant. This theoretical circuit has no resistance, so no energy is lost to heat. Resistance is like friction, so the total energy is constant. Du by dt equals 0. So du by dt equals d by dt of this. Take out all the constant bits, L over 2 d by dt of I times I. That's I times I plus 1 over 2c d by dt of q times q. So that's L over 2 I di by dt plus di by dt times I plus 1 over 2c q dq by dt plus dq by dt times q. So du by dt equals 2L over 2 I di by dt plus 2 over 2c q dq by dt, which equals L I di by dt plus q over c dq by dt. Remembering that du by dt equals 0 and I equals dq by dt and di by dt equals d2q by dt squared, we get du by dt equals Li d2q by dt squared plus q over ci. Dividing by I gives L di d2q by dt squared plus dq plus q over c equals 0, and rearranging gives d2q by dt squared equals minus q over lc, which equals minus 1 over lc times q. And then we say, let's look at this. This looks a bit like our spring equation. We add d2x by dt squared equals minus k over mx, which equals minus omega squared x, which we saw for the mass in a spring. And so for the mass in a spring, we said omega equals the square root of k over m, and the solution was that. And so we say, by analogy for an RC circuit, Q equals Q over m cosine omega t plus that, where omega equals that, and that, and that. Differentiating, we get that. And frankly, I don't do anything with that. Okay, maybe I should, but I don't. So know it's there, and know that we can use that analogy, and we'll pull out bits of it from various places. Okay. So what do you need to, oh man, should have done that, discard, we'll go back. So what do we need to know? We need to know those two. That one, that one, that. Okay? Let's have a look. What time do we start? At 2? So why don't we, ooh, that was lucky.